Let us consider 1 mole of MpXQ salt. Our goal will be to show that the following expression of gamma plus minus in terms of gamma plus and gamma minus is correct. To do so, we will derive on the present slide an expression for the free energy of 1 mole of salt dissolved in water in terms of the activity coefficients gamma plus for the cation and gamma minus for the anion. On the following slide, we will obtain a second expression for the free energy of 1 mole of salt dissolved in water using gamma plus minus, the mean activity coefficient. Comparison of these two expressions will lead to the desired relationship between the mean activity coefficient and the individual activity coefficients for the anions and the cations. We first write that the free energy G sub m for 1 mole of MpXQ salt dissolved in water is equal to the sum of P times the chemical potential mu plus for the cations and Q times the chemical potential mu minus for the anion, since there are P moles of cations and Q moles of anions per mole of salt. We then express the chemical potentials of the cation and anion in terms of their standard chemical potentials, mu0 plus and mu0 minus, and in terms of their respective molalities and activity coefficients. Note here that I did not bother to include the standard molality term B0 in each of the chemical potentials, as these would cancel out later on. This was done only to try and keep to a minimum the number of terms appearing in these equations. Then we use a relationship natural log of x times y equals natural log of x plus natural log of y to rewrite the terms log of gamma plus b plus and log of gamma minus b minus. For the next step of this derivation, we use the relationship a times natural log of x is equal to natural log of x to the power a. This allows us to rewrite PRT log of gamma plus as RT log of gamma plus raised to the power p. The same operation is then carried out with the term QRT log of gamma minus. In the final step, we combine the terms RT log of gamma plus raised to the power p and RT log of gamma minus raised to the power q to obtain RT log of gamma plus raised to the power p times gamma minus raised to the power q. Here again, we used the relationship log of x plus log of y equals log of the products xy. We now obtain a second expression for the free energy of 1 mole of salt dissolved in water using gamma plus minus, the mean activity coefficient for both the cation and the anion of the electrolyte. We follow the same approach as on the preceding slide. The only difference lies in the use of gamma plus minus. First, we write the free energy Gm for 1 mole of MpXQ salt dissolved in water as the sum of P times the chemical potential mu plus of the cation and Q times the chemical potential mu minus of the anions, since there are P moles of cations and Q moles of anions per mole of salt. Second, we write expressions for the chemical potential of the cation and for the chemical potential of the anion using the mean activity coefficient, gamma plus minus. Third, we rewrite each log of gamma b terms as log of gamma plus log of b for both the cation and the anion. Fourth, we rewrite PRT log of gamma plus minus as RT log of gamma plus minus raised to the power p, and do the same for the QRT log of gamma plus minus term. Finally, we rewrite the sum of natural logarithm as the natural logarithm of the product. Now we can compare the expressions obtained for the molar Gibbs energy, Gm, on the previous slide and on this slide, and conclude that gamma plus minus raised to the power p plus q must be equal to gamma plus raised to the power p times gamma minus raised to the power q, which leads to the desired relationship between gamma plus minus, the mean activity coefficient, and gamma plus and gamma minus, the activity coefficients for the individual cation and anion.